This lecture is for ELEC 1510 Logic Design. This is Lecture 11, Part 1 on binary adders, corresponding to textbook section 4.5. Let's review binary addition. If we have a single bit system, there are 4 possible addition operations that can occur. The first being 0 plus 0, which gives us a result of 0. The second being 0 plus 1, giving us a result of 1. The third being 1 plus 0, again giving us a result of 1. And the final being 1 plus 1, which gives us a 0 with a carried 1. What we want to do in this lecture is design hardware that will perform this operation. We have 2 inputs, the first bit input, the second bit input, and 2 outputs, the sum and the carry. So we're going to call these X, Y, S for sum, and C sub out for the carry out. So this block that takes 2 bit inputs, X and Y, and has 2 outputs, S and carry out, has a truth table that looks like this, is called a half adder and has a truth table that looks like this. When X and Y are both 0, the sum is 0 and the carry out is 0. When X and Y have a single 1 in the inputs, the sum is 1 and the carry out is 0. When X and Y are both 1, the sum is 0 and the carry out is 1. So now we can write out logical expressions for sum and carry out. We could use a K-map, but this is far too simple to need something extravagant like a K-map. We can just say that the sum is equal to x prime y or xy prime, which could also be written as x exclusive or y. And the carry out bit is going to be equal to x and y. So when we draw the actual hardware circuitry, I'll draw the sum as an actual sum of products circuit. We have x prime y and xy prime being added together, producing s at the output. And the carry out bit is just the AND function of x and y. So this combinational circuit right here is called a half adder block. Additionally, we can define something called a full adder block that also has a carry in. So if we have a carried bit from the last operation, say we added 1 and 1, and we got 0 with a carried 1 right here, well, now we've got a carry in, and we have to take that into account. So I'm going to assume in all of these operations that I have a carried 1. In the first operation, 1 plus 0 plus 0 is 1. 1 plus 0 plus 1 is 0 with a carried 1. 1 plus 1 plus 0 is 0 with a carried 1. And 1 plus 1 plus 1 is 1 with a carried 1. So now we have a full set of additional operations. The full adder truth table looks like this. We now have, in addition to the inputs x and y, a carry in bit. So a full adder has an additional input as compared to a half adder, but the same outputs carry out, and this should be s. So now we need to write out logical functions for carry out and s based on carry in x and y. The K-map for the s output with respect to inputs x, y, and carry in is going to look like this. which is going to produce the logical function x prime y prime carry in, or x prime y carry in prime, or x y carry in, or x y prime carry in prime. That's not a very simple function. Obviously, we can't combine any of those ones, so the function ends up being fairly complicated. The carry out bit gets optimized in the following way, and we will produce the function by circling bubbles equal to xy or y carry in or x carry in. Okay, so drawing the hardware for the full adder, x prime y prime carry in, x prime y carry in prime, x y carry in, and x y prime carry in prime. The carry out bit is the sum of 3 multiplications. The first is xy. The second is y carry in. And the third is x carry in. And this hardware is what we would call a full adder block. So now let's say that we want to create a 3-bit adder hardware block. Well, let's take a look at the first least significant bit addition. There's no potential of a carry in that can happen there. And what happens when we add these together, 0 plus 1 is 1 with a carried 0. 0 plus 1 is 0 with a carried 1, and 1 plus 0 is 1 with a carried 0. So what ultimately we can do is call our two inputs as x sub 2, x sub 1, and x sub 0. So that would correspond to this 0, this 1, and this 0. Additionally, we have inputs y sub 2, y sub 1, and y sub 0. Now, the inputs x sub 0 and y sub 0 don't have the potential of a carried in, so we will use these as inputs to a half adder block with outputs sum 0 and a carried output. Now, x sub 1 and y sub 1 will be inputs to a full adder. Where the carry out from the half adder is also the input as the carry in bit. And then we get outputs sum sub 1 and another carry out. Again, we use another full adder block for the most significant bit, where once again we use the carry out from the previous stage as the carry in of the more significant stage, and the output here is sum sub 2. And the carry out here is just left as an additional bit that you can use for something else. We don't use that as the input to anything else. Now, in general, when designing computer hardware, we try not to design too many blocks. So designing both a full adder and a half adder can be expensive. Sometimes you want to just design a single block. The way that you can modify this 3-bit adder to only use full adder circuits is to change the half adder to a full adder block and use a 0 as the input to the carry in, just so you never get a carried bit in that least significant stage.